Hello and namaste to the new video of the series second order linear differential equation. In this video we'll discuss about the second order linear differential equation but of special cases, that is called Cauchy-Euler equation. Prior to this video I have already discussed about the methods of solving the second order linear differential equation, especially in the case of constant coefficient for both homogeneous and the non-homogeneous one. And this video will be particularly focused for the Cauchy-Euler equation. Cauchy-Euler equation is also a type of second order linear differential equation, but the difference is it is not a constant coefficient equation. Okay, so if you see this equation is called the Cauchy-Euler equation. Cauchy-Euler equation, obviously. Let me write this once again. If you have second order linear differential equation, suppose this is our second order linear differential equation, let's say fx somewhere, and if we have a, b and c here, this will be called as constant coefficient. But in our case now we will have something rather than the constant coefficient. For the second order term we'll have x square. X square means we'll have the x polynomial with the degree 2. For the y single derivative term we'll have x, and for y with no derivative will not have any variable. And this form of equation, this form of second order linear differential equation, this is called Cauchy-Euler equation. Cauchy-Euler equation. For simplicity, let's say a Cauchy-Euler equation is a linear differential equation in which the coefficient of each derivative is a power of independent variable corresponding to the order of derivative. Okay, so for the second order, the Cauchy-Euler equation form is as shown here. And if this fx is equals to 0, if this fx is equals to 0, then this is called homogeneous. This is called homogeneous Cauchy-Euler equation. And in this video we'll discuss about the homogeneous Cauchy-Euler equation of the second order form only, how to solve this by using the different methods. Okay, so I'll show you the example how to solve it. You have the two ways of solving it. The one is like assuming the solution is in the form of y equals to x power m. We assume the solution in the form of y equals to x power m and get our auxiliary form. And once we get our auxiliary equation, we'll solve it for the roots, and for the different cases of the roots we'll have the different solution of the differential equation. Okay, and the next is by assuming your dependent variable x to be exponential power t, and converting this Cauchy-Euler equation into the form of constant coefficient equation. I'll show these methods in the following example. For now, let's talk about this getting the solution from the form of y equals to x power m. Okay, so if y is equals to x power m, then if we assume the solution to be y equals to x power m, then everything from the y, that is the derivative of y and the y itself, should satisfy this differential equation, right? They should satisfy this differential equation. So we'll have y prime is equals to m x m minus 1, right? So our y double prime will be nothing but m minus 1 x m minus 2, right? So putting them everything back to this equation, we'll get a m, let's say a x square will have m minus 1 x m minus 2 plus next will be b x m x minus 1 plus we'll have c x m is equals to 0. So here you will have a, this x square and the denominator x square from here will cancel out. This x will cancel out with the denominator x from here. So we'll have ultimately a m minus 1 x power m plus b m x power m plus c x power m equals to 0. Taking x power m as a constant, we have a m minus 1 plus pm plus c equals to 0. Since this x power m can't be 0 because we are solving for we are expecting the non-zero solution, so this x power m can't be 0. That means this will be our 0. which implies this equation to be 0, right? So this is our index equation. This is also called index equation, or sometimes auxiliary equation also. And once we get the roots of this auxiliary equation in the second order differential equation, it will be the quadratic roots. And once we get the quadratic roots, for the different cases, the roots will have the different solution. This is the one method. Okay. And also remember, the Cauchy-Euler's equation is also called equidimensional equation also. Okay, this is also called equidimensional equation. Okay, let me discuss more about this. So on the basis of the solution, on the basis of the roots you have the different cases of the solution. I'll discuss this by an example. Let's go to the one example. So you have the differential equation in this form, and you need to solve this differential equation. First, determine whether this differential equation is in the form of Cauchy-Euler's equation, or is it it is like constant coefficient equation. So looking at this, we can conclude that this is Cauchy-Euler's equation, or the equidimensional equation of second order. So we can solve this by assuming y equals to x power m, and if we assume y equals to x power m, our y prime will be nothing but mx power m minus 1, and our double y prime will be m minus 1 x m minus 2. Putting everything back to the given ODEs, and since x power m can't be 0, we'll end up with something like okay, let me write everything here. I will have x square, I will have m minus 1 x m minus 2, right, plus I will have 2x mx minus 1 minus 6 xm equals to 0. And here this x square will be cancelled out from the denominator x square here. This x will be cancelled out from the denominator x from here. That means we'll end up with something like m minus 1 plus 2m minus 6 equals to 0. This is our index equation, the quadratic form obviously. So this will give me m square minus m plus 2m minus 6 equals to 0, which can be further simplified into m square plus m minus 6 equals to 0, and my solutions will be m equals 2 and m equals minus 3. Okay, these are my solutions. So the case is like you have the two roots, they are unequal and they are real and unequal roots. So if you have remembered our previous video, we have discussed the different three cases for the constant coefficient homogeneous second order linear equation also. So it will have also some type of similar form. So if the case is real and unequal, then our solution will be y equals to c1 x power m1. will have the two solution, m1 and m2. Another will be c2 x power m2. So this will give me c1 x power 2 plus c2 x power negative 3. This will implies x square plus c2 over x power 3, and the value of c1 and c2 will be determined by using the initial condition or the boundary condition. For now, the general solution is this. So this is the case of having unequal and real roots of index equation. So we have already solved this case, right? Now what if we have the repeated roots, and what if we have the complex root? I'll come of this later. So for now, let me solve the same equation but by using the different methods. Different methods means just by changing this form into the constant coefficient equation form. So for that, what I have to do, I have to assume my dependent variable x is equals to exponential t, and while if I just interchange my dependent variable, then I will get the constant coefficient equation. This is how the Cauchy-Euler's equation is designed. Okay, so x equals to exponential t means we have t equals ln x, or let's say log e base x. Okay, logarithm x. Now we are converting now x into t, right? We are converting whole dependent variable x into t. So we have y here, we have now t. We'll have the differential equation in the form of y and t. T will be our independent variable and y will be our dependent one. So to convert this one, if you assume these things, then you will have dy over dx, or let's say x dy over dx. This will be nothing but x dy over dt by general dt over dx. This will give you x dy over dt into dt over dx means d log x over dx, and this will be nothing dy over dt into 1 over x. This will give you dy over dt. So your x dy over dx will be converted into dy over dt. And similarly, if you follow the same general method, you will get x square d square y over dx square is equals to, let's say this is x square d by dx dy over dx, right? So I will have nothing but x square. This will be my d over dt, let's say d. This will be my dy over dx, can be also written from this equation is dy over dt into 1 over x, and here you will have using general dt over dx. 1x will be already cancel out, so x d over dt dy over dt 1 over x. And if you okay, let me do everything here. So if you use the product rule and try to get the solution, you will have d over dt, let's say you'll have dy over dt 1 over x plus x, we'll have dy over dt, and the next will be d over dt, but this time you will have 1 over x, and your x is nothing but exponential t. So this will give you this x cancel out, d square y by dt square negative, okay, x dy over dt into exponential minus t. Okay, so this x and exponential minus t will be cancel out, because ultimately exponential negative t means 1 over x. So the end will be d square y dt square dy over dt. You can just memorize this if you want your solution to be faster. Okay, so ultimately what I have is, let me erase everything and write here. What I have is my x dy over dx will be nothing but dy over dt, and my x square d square y over dx square will be nothing but d square y over dt square negative dy over dt. That is what we'll expect after substituting this. So we have now our equation x square double y prime plus 2x y prime minus 6y. Now let's put everything we have here. X square y prime will be d square y over dt square negative of dy over dt. Our 2x x y prime will be nothing but dy over dt negative 6y equals to 0. So this will ultimately be d square y over dt square plus dy over dt negative 6y equals to 0. And don't forget that we have put x is equals to exponential t. Okay, now this is our second order linear differential equation, and if you have remembered, this is our constant coefficient, as we have discussed in our first video of this series. This is constant coefficient, and the dependent variable here is t, and the independent variable here is t, and the dependent is y. Okay, so variable t, let's say y is the function of t here. Okay, now since this is our constant coefficient homogeneous differential equation, we can easily get the solution by just converting this into the auxiliary equation of m. So you can just directly write the auxiliary equation from this constant coefficient differential equation. That will be m square plus m minus 6 equals to 0. This can be solved to get the roots. M square plus 3m minus 2m minus 6 equals to 0. This will be m plus 3, m minus 2 equals to 0. That means m will be 2 and negative 3, right? So since we have the two unequal real roots, and we have the solution for the homogeneous equation in the form of c1 exponential 2t. Here the independent variable is t, right? And the next will be c2 exponential minus 3t, right? But our question has asked with the independent variable of x, so we have to convert the t into the x ultimately. So you will have our t is nothing but ln x, 2 ln x plus c2 exponential minus 3 ln x. This will give you c1e ln x square plus c2 exponential ln x negative 3. This is finally c1 x square plus c2 x negative 3. Okay, so this is how we get the same answers that we have obtained in previous method. So you have the two options. Either you can solve but directly by assuming your solution is y equals x power m, or you can just substitute your independent variable x to the t and make the form of constant coefficient and solve for constant coefficient homogeneous differential equation and ultimately get the solution in the form of x. That's how we can solve. Okay, let me go to another cases that we may have for the different roots condition. So our differential equation is given in this form. We'll assume our y is x power m. Okay, so this will leads me again to x square, y double prime will be nothing but m minus 1, and I will have 3, this will be m just m, and I will have 4 equals to 0. I assume that you are quite familiar with this equation now. So this will be m square minus 4m plus 4 equals to 0. This will be nothing but m minus 2 square equals 0. That means m equals to 2 comma 2. We have the two roots, but both of them are equal. And if the roots are equal and you are assuming your solution y equals to x power m, then your direct solution will be in this form. We'll have y equals to c1, and since they are the repeated roots, we'll multiply your next term with ln x here, and the final will be x power m. That means your solution here will be y equals to c1 plus we'll have c2 ln x, and this will be multiplied by x power m. X power m means c1 plus c2 ln x power m means here x square. That's it, very easy. Or you can just try by using the substitution method of the independent variable also. Okay, let me do one more question. This is in the form of, again this is in the form of Cauchy-Euler's equation of the second order differential equation, and you can again use the method of y equals to x power m solution. So this will lead to the index equation m minus 1 plus m plus 1 equals to 0, which will give you m square minus m plus 1 equals to 0. This will be m equals to plus minus I. So you have the conjugate roots, that means you have the imaginary and the real parts. You have the complex roots, and if you are having complex root, you always have some imaginary part plus some imaginary and real parts, right? For this particular case, you have alpha equals to 0 and your beta is here 1, right? So whenever you have the conjugate roots and you are assuming your solution is y equals to x power m, and for this case your solution will be given by this equation. This equation means y is equals to x power alpha c1 cos beta ln x plus c2 sin beta ln x. That means you can just write here everything. Your solution will be exponential alpha c1 cos beta ln x plus c2 sin beta ln x. Great. Okay, so your alpha here is exponential 0, so your c1 cos your beta here is 1, c1 cos ln x plus c2 sin ln x. This will be your solution. Your exponential 0 is 1. Okay, so this will be your solution. This is quite straightforward. I think I will stop here. In the next video of this series, I will come up with how the methods, how we can solve the non-homogeneous Cauchy-Euler equation. Till then, stay tuned. Thank you very much.